Sir, not audible.
So we have started the terminologies in the graph. So we're having 5 types of terminologies over there. One is adjacent node or vertices, and path, connectivity, and degree of node and complete graph. So you have in the previous class itself, we have told what is meant by adjacent node. If the node that has been having the neighbors with the edges, then that node will be that type. That no, all the nodes will known as the adjacent node for that particular node. That means vertices. And the path, sequence of vertices in which each pair of successive node is connected by an edge. So all the pair want to be connected by the edge. So that is known as the path. And the simplest path, which will be a path, is simple if all of its vertices are distant. So it means the simplest path you want to find out. So that is one of the terminologies over there. And simple path, which may be consist of the n number of node, it will be traversed from one node to another node. The minimum number of node that can be known as the simple path. And this closed path, I have already told you, the first vertices and last vertices can be repeated, and remaining all the nodes, all the vertices will not be repeated. So that type of path is known as the closed path. And this is the connected path. So as of till now, we have the till closed path we have discussed in the previous class. So next one, it will be a connected graph. So the graph is said to be connected if there is a path from any node to any node. So here you can see whether this is a directed path or undirected graph. In this example, whether this is a directed or undirected. Undirected graph. So undirected graph, which will be consist of the bidirectional graph. We can traverse from any node to any node. So in this case, this all node, which will be the connected graph, you can traverse from one node to any other node in the graph. So if you want to traverse from B to G, whether it is possible?
Yes, sir.
Yes. When you want to travel from B to D, yes, the traversals also which will be possible. So if you are traveling from one node to all other node in your graph, then that graph is known as represented as the connected graph. And here you can see some of an example of disconnected graph, whether the graph has been connected, whether we can traverse from B to G.
No, sir.
No. So while you are setting a neighbor node in your graph representation, while you are setting a neighbor node, you want to set the neighbor node for you want to set the neighbor node of A is B, C, and D. If you are not setting the neighbor node as C, then that graph will be represented separately, and some part will be represented separately. There will be no connection in your graph. So this kind of graph will be this kind of graph also will be occur in your program. So this type of graph, which will be consist of a disconnected graph. So once you are finally getting those output, and after getting the output, if you are seeing that all the nodes has been connected for all the nodes in the in the undirected graph. And next one, it will be a weakly connected and strongly connected. Can you differentiate between this weakly connected and strongly connected by the seeing those image? Can anyone, by seeing this image, whether this is a directed or undirected graph?
Directed.
Directed graph. So in the directed graph, we having a two types of connecting techniques will be there. One is weakly connected and another one is strongly connected. So now by seeing those examples, you can tell me why it was weakly connected and why it was strongly connected.
Sir, weakly connected is not closed. It's not a closed.
Weakly connected is
not a closed.
it was not closed, right? Yes.
We cannot go to the every node from the single node. So that means A to E we cannot. We can go
Yes.
in one direction, but in
Yes.
strongly connected, we can go in many directions.
Yes, good. So in the weakly connected, all the nodes want to be equivalent. If suppose if I want to go from A to B, I want to go, whether it is possible there. in the weakly connected. This is a directed graph, so this is not a bidirectional graph, so it is a directed graph, so it means it will be representation of the direction. So I want to go for A to B. So whether it is possible in the weakly connected picture?
No, sir.
No. So same picture has been given there, but I have connected some of the graphs, some of the links or edges over there for the vertices. So if suppose I want to go with A to, I want to go from A to B, whether it is possible?
Yes, sir.
In the strongly connected, you can see here, I will travel from A to C, C to D, C to B. So I can traverse from, so all the node I can travel. So here some of the nodes I can travel, some of the node I cannot able to traverse. So this kind of graphs which will be represented as weakly graph, and all the nodes which will be possible to traverse is known as the strongly connected graph. And next one is the degree. So to find out the degree of a node or a vertices, so number of edges connected to it. Can you tell me for this C, how many edges has been connected?
3, sir.
3 edges. So that we have discussed already in the previous class, I hope so. So degree graph which will be conducted of 2 types. One is undirected graph degree and the directed graph degree. So here you can see this degree of node is equal to number of edges connected to it. So this is an undirectional graph, whether it is in degree or out degree, that you want to calculate. So this is a bidirectional graph, so you want to calculate all the degrees. So if suppose I am going to calculate the degree of E, then the degree will be 2, right?
Yes, sir.
Yes, sir.
Yes. So this is a degree of a graph. And next, degree for the directed graph. Degree for the directed graph, which will be consist of 2 types. Because why? Because the directed graph which will be represent the direction of the all the vertices. So here, in degree of a node and out degree of a node you want to calculate. In degree is a number of edges coming to that node, and out degree of the node is equal to number of edges going outside from the node. So can you tell me for A, what is the in degree?
1, sir.
1. So what is that? From C vertices to A vertices, there is only 1 degree number of edges coming to that particular node, right?
Yes.
Yes. So for that A, what is out degree of a node?
2, sir.
2.
So the out degree, A to B and A to D. So 2 out degree for this particular A. So this is the directed graph techniques. That is degree of directed and undirected. You want to find out the degree for each and individual node. So that is only one line concept in your programming. So that you want to find out the degree of a directed and undirected graph. So here, if you are going with the directed graph, there will be 2 types. One is in degree of a node and out degree of a node. So that will be a 2 types. And here, the final graph, which will be a complete graph. A complete graph is a graph in which each pair of a graph vertices is connected by an edges. So can you tell me the difference between the complete graph and the connected graph?
Sir, in complete vertices, it's
number
connected to all vertices.
In complete graph?
Vertices is connected to all vertices.
Yes, one vertices, if you are taking one vertices, that will be connected to all the vertices. But here you can see in connected graph, not one vertices will connect from all the vertices. By the path, it will be connecting over here. By its path, it will be connected in the connected graph. But here in a complete graph, all the vertices will have the equal degree that will be traversed to all the vertices, remaining vertices. So if suppose you are taking A, you can see how many edges are there for A.
4.
4. So it will be traversing to B, C, D, and E, right? So remaining all the vertices has been traversed from A. So likewise, you can take the example of E. So E is my vertices. I want to travel from E to all the vertices. Whether it is possible to travel from E to all the vertices?
Yes, sir.
Yes. So likewise, you can see the D. So it means that if you are having 5 vertices, for each and individual vertices, it want to traverse 4 times. It want to traverse 4 times. If suppose your final graph is like this, then that graph will be represented as your complete graph. Clear about this types of graphs? So terminologies of graphs. So mostly they will ask you in a 2 mark. That's it. What is that? What is that? Give you an example for this. That's it. So terminology of a graph. The terminology, the program will be there for, I hope so. Graph representation and the traversal. Yes, the program will be there for this terminology. But in the programming concept, that will be very easy when you are seeing this also. Have you understood that the terminologies of a graph, or I want to explain it one more time?
Understood, sir.
Understood.
Those who are telling that I have understood can raise your hands now. Raise your hands. I told you those who are understood can raise your hand. Those who are understanding the concept can raise your hands.
சார் ஜிமெயில் அட்டன் பண்ணுறேன்.
புரியல.
ஜிமெயில் அட்டன் பண்ணிக்கிறேன் சார் கிளாஸ், அதனால வைஸ் சான்ஸ் கொடுக்க முடியும்.
மொபைல்லையா?
ஆமாம் சார், ஜிமெயில் மீட்டில் அட்டன் பண்ணல சார். ஜிமெயிலில் வந்து ரைஸ் ஹேண்ட்ஸ் ஆப்ஷன்ஸ் இல்லை சார்.
ஓகே, ஃபைன். So rise down. So remaining are not understand. So that's fine. Good. So I hope so. Some of them are understand. Some of them are not understand. Fine. So now we will move with this. So this is the basic thing that we have discussed. Till now we have discussed only the graph ADT and the representation. Till now we have discussed only the graph ADT. Only graph ADT we have discussed. So as of now, the 2 classes we have discussed only graph ADT, the basic thing that we have discussed in the syllabus. Now we will go with the representation of a graph. So yes, first thing I want to mention before going to this topic, I want to mention this. Have I informed you how the tree structure will be stored in the system, in the database?
No, sir.
No. So it was not, the number will be wrong. Don't worry about that. The number will be wrong. So I have told anything related to the tree structure will stored in the array or a list or a stack or a queue. Have we discussed anything like that?
No, sir.
Yes. I'm asking that whether we have discussed anything like that. We have stored, the tree has been represented like this, right? So this is a tree. You can tell by the structure, you can tell this is the tree. Whether this kind of tree structure only the computer will store the memory?
No, sir.
No. So I am asking that whether I have told anything about the storing technique of a tree.
No, sir.
No. Yes.
Yes, sir. No, sir.
Yes. No. Yes.
No, sir.
Yes. Thank you. Not discussed it. So let me discuss this. So first of all, before going to the representation of a graph, first we will discuss this. The computer will not take any image representation or the tree representation or the any representation they won't take to store that particular elements on the node for the memory. So you clear about this, right? The computer will not take any representation to store this particular node in the computer memory. So memory in the sense it will be coming of data, a number of data list will be there. So in this list they want to be stored. In the hashing technique we have done that how the elements will be stored inside the memory. So likewise, the tree format also, there is a proper structure to store that memory in the list or a stack, whatever it may be. So this is an image representation to understand the concept, but not to store in this computer memory. So in the final step, I hope so, in the heap tree concept, I have told you that it will store from level 0, level 1, level 2. Likewise, it will be changing over there, and it will be storing an element 2, 3, 4, 5, 6, 7, 8, 9, so on. And after that, if you want to find out the child node of this, I have given some of the formula to find out the child node of this, and formula to find out the parent node of this particular 4. Have you remembered that?
Yes, sir.
Yes. Have you remembered that?
Yes, sir.
Yes, sir.
Yes. Yes. It means that we have discussed that. Am I right? Where is that? I can't get those things. It means that we have discussed that, but I am not having those copies. But we have discussed that. So we're having some of a formula to find out the child node. We want to represent in a list by taking the level 0, and we're having some of a formula to find out that is 2 into I something. The formula will be there. We want to find out. Yes. So based upon this formula, that the storing purpose will be starting from level 0, level 1, and level 2 for all the trees, and it will be storing in a list. And we want to find out those things. We can find out those things. So same as like that, we want to represent the graph also. So the graph which will be the element which will not be stored as like that, how you are mentioning in a graph, the element will not be stored as like that. So it will be having some of the representation to the computer memories to store that particular graph in the system. So then in that case, the graph will be using of 2 types for storing the elements. One is matrix and another one is list. So in these 2 types, the elements of the vertices will be stored in your computer memory. One is matrix and another one is list. Clear about this? Yes.
So this is for graphs or for trees, sir?
Tree, it will be storing in a list, but because it will be in a hierarchical order, the graph is not in a hierarchical order. So it will be taking level 0, level 1, level 2. So it will collect all the root node first, and after that it will collect the child node, and after that it collect the subchild node. Likewise, it will be collecting all the elements in the sequence order. But in this case, you cannot find out the sequence order right in a graph.
Yes, sir.
Yes. So in that case, you can store, the computer will store the elements and the vertices either in a matrix form or in a list form. That will be depends upon how many vertices you are having and how many connections you are having for each and individual vertices. That is the thing. In a tree, don't confuse about that. In a tree, it will be storing in a list form only, because it will be coming in a hierarchical order. So no worry about that. So it will be storing all the elements over there. But in a graph, it was not in a hierarchical order. So it means that some elements will having a connection with some elements will not have the connection with some elements. So for this, in this graph representation, we are going with 2 types of representation of a graph to store that particular element of a vertices. That means a matrix and the list. So it will be interesting, I hope so. When you are coming to the next slide, it will be interesting. So before going to the storing an element, the adjacent matrix, so that will be called as an adjacent matrix. So you want to create K into K matrix. K in the sense how many nodes, how many vertices you are having. In that vertices you want to create, if I am having 5 vertices in my graph, I want to create 5 into 5 matrix. You all know how to create the 5 into 5 matrix, right?
Yes.
Yes. And row and column represent the nodes of the graph. So it means the vertices of a graph. The row and column represent the vertices of the graphs. And if edge is present, then store 1, otherwise store 0. That is the concept. If edge is present, you want to store 1, otherwise you want to store 0. Clear?
Yes, sir.
So this is my graph first. What is the first condition for adjacency matrix?
Form K into K minus
How many
So
vertices?
how many vertices are there?
5, sir.
5.
5 vertices. So 5 into 5 matrix like this: 1, 2, 3, 4, 5. Am I right?
Yes, sir.
1, 2, 3, 4, 5. So what is the second point? What is the second point? So we have created find to find matrix, and row and column want to be represent the node of the graph. It means vertices of the graph. So here it will be the rows and here it will be the columns. It want to be represent the vertices of a graph. What is the vertices here?
0, 1, 2, 3, 4.
0, 1, 2, 3, and 4. Am I right? So row will be 0, 1, 2, 3, 4, and this will be 0, 1, 2, 3, and 4. Am I right?
Yes, sir.
Yes. What is the third point now?
If edge is present, 1.
If edge is, who is there? Yes. What is the third point? If edge is present, then we want to represent 1. If edge is not present, you want to represent 0. Am I right?
Yes, sir.
So here you can see this is my node vertices. This is my vertices. 0 to 0, any edges is there. So it means if it is, the graph will be like this. It will be the self edge, self connection. If it is there, it will be a self connection. So here you are not having any self connection over here. Whether 0 to 0, are you having any vertices?
No, sir.
Edges? No. So you want to represent, you want to give the value as 0. 0 to 1?
Yes, sir.
Yes, 0 to 2? 0 to 2?
2.
0 to 2, direct
Zero.
vertices.
No,
0. 0 to 3?
Zero.
0. 0 to
sir.
4?
No, sir.
0.
One.
Yes, sir.
1.
0 to 4? 1.
One.
Yes. So likewise, you can fastly tell me 1 to 0.
One.
1.
1.
1 to 1,
0.
0.
0.
0.
One.
1. Sir, 1 to 2, 1, sir.
1 to
Sir,
2,
all
it will be 1.
1, 1,
1.
1. 1, 1, 1, sir.
Okay. Now 2 to 0.
0,
Zero.
1,
0. 1.
1,
0.
0,
1. 0.
0. 0,
0.
1,
One.
1,
One. One.
1.
1. 0, 1,
Zero.
sir.
1.
1.
0, 1,
1.
1.
1.
1,
0.
0,
1.
1,
0.
0.
So, yes. So this will be the matrix representation. So likewise, if you are giving the nodes with the vertices, this will be the matrix representation. You can do a matrix representation or a list representation. In this case, so this will be like this. The data will be stored in your computer memory. So it means that if you are having the node, you are having the vertices over here. In this vertices, you having a number of vertices connections. In this connection, particularly this vertices making how many connection to this vertices. You can see here the 0 will making only 2 connection in the all remaining vertices, right? So it means 1 and 4. It will be making a connection of 1 and 4, right?
Yes, sir.
Yes, sir.
Yes. So likewise, you can go with any one of the vertices and you can find out whether how many connection for there in a vertices. In your exam point of view, they will give you a matrix form with you, and they ask you to structure a graph. You just imagine there will be two types. One thing, they will give you a graph and they ask you to do a matrix calculation. Otherwise, they will give you a matrix calculation and you want to structure a graph. If suppose I am giving this matrix structure and I want to asking you to design a graph like this, then based upon the connection, you want to design the vertices and you want to design the edges also. Have you understand? Am I audible?
Yes, sir.
Are you getting what I am telling now? So in the exam point of view, mostly they won't ask. If they are asking, they don't get confused. So if they are giving this matrix over here and ask them to draw a graph, then you want to represent this graph with this structure image. So that is the thing. So now, so this is the finding out the adjacent matrix. Now you can take any. So here this connection. So before that we have seen the undirected graph. So this is a directed graph. Am I right?
Yes, sir.
Yes, sir.
Yeah.
Yes. So this is a directed graph. How many vertices are there? 1, 2, 3, 4, 5, 6, 7. So
7.
7 vertices. So 1, 2, 3, 4, 5, 6, and 7. So 1, 2, 3, 4. Yes. So this is the 7 into 7 matrix we have designed. First step we have designed the 7 into 7 matrix, and after that, what is the next step?
Row and column.
Row and column. The
Rows
row
and
will be your vertices A, B, C, D, E, F, and G. So here also same A to G will be there. A to G. Now you can give the connections for this. So here A to A, any traversal is happening?
No, sir. 0.
No.
No, sir.
So A to B,
1.
1.
A to C,
1.
1, and remaining all it will be 0, right?
0.
Yes, sir.
Yes. So now coming to B to A, either any traversal is
sir.
happening? No.
0.
So B to B also no, and B to
C
C
also no.
no. B to D
D,
yes
1.
was.
E1.
So it means that we have given the directed connection, directed graph. In this directed graph, the graph will be representing the direction. So based upon that direction, you want to work it out and you want to give those things. And you can see that the differentiate of these two things, right? So if you are taking an example of this, here most probably all the elements will be become 0. Am I right? For the directed
Yes,
graph, most probably all the elements will be become 0. Only some of the elements will be become 1. It means we are directed. Only we are using the directed graph. So in this undirected graph, you can see here the most element will be become 1 and some of the element only become 0. Am I right?
Yes, sir.
Yes. So in this case, the computer's memory, when you are going with a directed graph or an undirected graph, what about the computer memory? Whatever we have stored as 0 in your matrix representation, that memory will be the wastage of the memory. Am I right? Yes.
Yes, sir.
This all the things, that means this 15 data will be stored in your memory. Wherever the 0 has been represented in your memory, that memory is automatically known as the wastage of your computer memory. Am I right?
Yes, sir.
Yes. So for this, so I will go with one more example also. So now, so what is this graph means?
Weighted graph.
Weighted graph. So this is a weighted graph. So how many vertices are there?
5.
5 vertices. So what is my vertices all?
A, B, C, D.
So now tell me, A to A,
0.
0. A to B,
1.
10.
1.
Say 1.
here in the weighted graph, you want to mention the weight of the graph.
10.
10. In the weighted graph, you want to mention the weight of the graph. It means if you are giving any weight for this, it means if you are giving any weight in your graph, it means that automatically it will means that we having a connection between A and B. For either storing that value called 1, we are storing the weight of 10 or whatever it may be. If you are storing any values apart from 0 over here, then that numbers will be stored and that connection will be automatically made. We having a connection between A and B. Are you getting this? So if suppose A to C,
5.
5.
5. A to D,
4.
4.
4. A to E,
0.
0. So B to A,
10.
10.
10. Because it is a undirected graph, so that way it will be travels from both end. So B to B it will be 0. B to C,
0.
0.
B to D,
7.
7.
7. B
3.
to E, 3.
3.
B to, so here you likewise you want to fill those things, and after finalizing, and you can see all the graphs representation in a matrix format. After you having a 3 graphs in a represent format, you can easily find out whether this is a directed graph or an undirected graph or a weighted graph. Am I right?
Yes, sir.
Yes. How you will find out that?
Sir, if 1 is more, it is
Undirected.
Undirected graph.
Yes. Good.
undirected. 1 is
Yes.
0 is
If more zeros
means
are there,
undirected.
then it is
Directed, sir.
directed graph.
Directed graph. Yes.
Any
If
numerical
numbers is
values
there
other
means
than
it is
0 and
weighted.
1.
Good. Yes. So this is a basic structure, basic idea. Yes, is a good answer. So this is a basic thing that you, when you are representing and then when you are seeing a small element 5 into 5 matrix or 8 into 8 matrix, you can easily identify whether this is the directed, undirected, or weighted graph. If suppose you are using a 100 into 100 matrix or 200 into 200 matrix, then you can't able to see those matrix and you can tell that, right? For that also we will have some criteria to find out whether that is a weighted or directed, undirected, or weighted. That once we are going to the programming part, then I will explain you how to find out those things, right? So for your theory point of view, this is the thing. If they are giving any number, any values over there, and you want to draw the graph for that particular matrix, then you want to draw the particular matrix and you want to mention that whether this is a weighted graph or unweighted graph. Sorry, it is a directed graph or undirected graph or a weighted graph that you want to be mentioned in that. So that is the thing. So now, so whether this is the so what is the graph is this?
Undirected.
Undirected graph.
Undirected graph. So for this undirected graph, this was a representation of a matrix format. And can you tell me the wastage of the memory in this matrix format?
A to A to E.
Yes. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 10 memories.
11.
So
11.
11. Yes, 11 memories. So 11 memories has been wasted. It will not be used hereafter for in this kind of graphs. It is a only 5 into 5 matrix. So 5 into 5 matrix, it will be 25, right? Yes.
Yes, sir.
Yes, sir.
So 20 in this 25, we have wasted 11 memories over there. It means nearly we are wasting 50% of a memory. Nearly we are wasting the 50% of a memory of the system. Am I right? For this, overcoming this concept, if we are going with the list concept, so that is the only thing why we are going with the list concept. We can represent all the terms in the matrix format also, but the thing to overcome this wastage of a memory in the system, we are going with the list concept to store the list. How you want to store that adjacent node of that particular node. Here you can see here, this is the list representation. Am I right?
Yes, sir.
Yes, this is the list representation. Here I am taking this A colon. Have you studied anything like this A colon of values? Have you studied anything like this A colon of values? The PSPP. Dictionary, yes. It is a dictionary format. So in this, the list, we are using a dictionary over here. It means this A is my keyword and these are all my elements, and this keyword will not be changed, and this element can be changed by removing this path from this tree. But A will not be changed, but the element will be changed by removing this path. And here you can represent this matrix representation for overcoming the memory wastage. We can going with the list. In this list, we can apply this A is my keyword, and A with the adjacent nodes are B, C, and D. Am I right? Yes.
Yes, sir.
For this A, the adjacent node, it will be the traversing node from A will be B, C, and D. Am I right? So it means there is no wastage of memory. When I am going with this matrix format, I want to calculate for A and A and E also. So this two memory will be wasted for this calculation.
Yes, sir.
So same as like that, I am taking only the adjacent memory and I am storing the adjacent nodes in the list. So it will be consist of this. So if suppose I am going to take a B memory, so B, D, E, and A. Am I right? So three vertices will be there. So I am storing the three vertices A, D, and E. So here I am using the 5 memory allocation over here. So I want to allocate 5 memory and I want to represent 2 0 memories over there. It will be a wastage of memory. For overcoming this wastage, we are going with the list concept for this particular graph. Clear? So let's move with one more example. So yes. So now you can see what is this graph means.
Directed.
Directed graph. Directed graph. If you are using this in a graph representation, in the matrix representation, it will be 7 to 7 row, and after that, nearly 75% of the memory will be wasted. Only 25% of the memory will be used for the directed graph. So if suppose I am going with the list concept over here, I want to calculate the adjacent node of A. So it means B is my one traversal and C is my one traversal. Am I right? So it means B comma C. So we can save only B and C. That's fine. Yes?
Yes.
Yes. If suppose you are going in a matrix format, what we want to do? We want to allocate 7 memories over here to traverse from, 6 memories over here to traverse from A to all the elements, remaining all the elements. Here we are using only 2 elements that was connected from A. Yes?
Yes, sir.
Yes. So now, same as like that for B, it will be traversed to E and D. So we can take only 2 elements. So that's for C, there is no out traversal. So it will be empty list. Here also it will be empty. Here also it will be empty list, which will not cost any memory in your memory allocation. Empty list will not cost any memory in your memory allocation. But in the sense, if you are going with the matrix format, if it is empty, the C will be empty. What we will do is we will do all the nodes we will give as 0, right?
Yes, sir.
So
Yes,
it means that it will take a memory. There is no edges was there for a particular vertices called C, and for that purpose also we are using the memory. That means 7 memories. 6 memories you are using in a matrix format. For overcoming this, we are going to the list concept. So mostly we will do the list concept only in all the program. But the thing, the matrix also will be applicable for that. So that's why I'm explaining why this matrix will not suit for this particular storing purpose in this graphs and tree concept. So here the weighted graph, right?
Yes, sir.
Yes. So you can see here how the elements has been represented. In this weighted graph, the A will be traversed from A to B and the weight will be 5. So likewise, we can differentiate this. Yes. The A will traverse from A to C and the weight will be 4. The A will be traversed from A to D and the weight will be 10. You can see here, this is my 5, this is my 4, and this is my 10. Likewise, we want to calculate for all the nodes. So this is the weighted graph techniques to implement the list. Clear?
Yes, sir.
Yes.
clear, sir.
Yes. So this is the thing. So array representation, the list representation, you already know that. And here, how you will store those in your program, that is the thing. So I have told you that we will store like this. So I have theoretically I have told you that I will store in this A representation, I will store this 2. This 3 will be stored in the A representation. Before that, we have studied any matrix program in your PSPP or in the data structure program, data structure subject.
No.
We have not yet studied the matrix program, right? Yes.
Yes.
So first we want to know how to design a matrix first, and based upon the matrix, we want to occupy this matrix number into a list. So here you can see an example. So here it is my list of node. So list of node which will be connected. That means A will be connected. A value will be like this 0, 1, 1, 1. So this will be, I will explain you when we are going with the programming concept. So the list will be prepared with the use of nested list. Have you heard about the name nested list? have you heard about the name called nested list?
Sir. No, sir.
No. Anyone? Have you heard about the name nested list?
Yes, sir.
Yes, we have studied the nested list in a PSPP. If condition, if you are going with in the list concept also, we have studied the nested list. Inside the list, you are going to create a list. Inside the list, you are going to create one list that is known as the nested list that we have studied already. We have studied. So here, what I will do is I will take all the vertices first as my list. So here, first I will take A, B, C, D, E. So this is my vertices, and this vertices. So here A will be calculated as my list, and inside the A list, I will create the path, whatever the A will be traveling. It means B, C, or D, whatever the path it was traveled by A, I will create the nested list here, and I will store the memory. I will store those things. So that we will discuss in the upcoming class. That's not a problem. So when you are going with the when you are creating a node in a programming part, first what we want to do, we want to create a node. How we have created a node for our tree, same like that we want to create a first node, and after that we want to initialize all the nodes with the adjacent nodes. We want to represent the adjacent node. So that is the thing. So before completing this class, I will show you an example of this. So this we will discuss when we are entering into the after completion of your lines of code, that we will discuss this. Yes, before completing this, I will show you an example. So this is the graph, basic representation of the graphs. Just forget about this lines of codes and all. So based upon this input, yes,
Not audible.
am I not audible?
Now audible, sir. Before not
Yes,
audible.
yes. So here V is my vertices. So you just imagine this is the program you want to do. Here V is my vertices, and you can tell me what is the first node I want to insert here. This means
5.
the add function. Add function is my first adding an element. So this is an object creation. You just forgot this and come to this line. What is the first node I want to add?
0.
0.
So we having 5 nodes. So 0 vertices will be there, 3, 4, and 5. So now I am going to add 0 in this. 0, 1, 2, 3, and 4. So I am having 5 vertices over here. So now I am creating an edge over here from 0 to 1. So in this is the thing. I am creating my adjacent node after creating my vertices. First I am creating a vertices, and after that I am creating my edges to the particular node. So here I have created 0 to 1. So I have created one edge over here, and again I am creating 0 to 4 one edge, and after that I am creating 1 to 2 one edge, and 1 to 3 one edge will be there, and 1 to 4 the edge will be there, and 2 to 3 the edge will be there, and 3 to 4 the edge will be there. So this is the graph structure that you are going to design. First concept, you are going to create a graph structure. So while seeing this, whether you can easily find out whether this is a graph representation or a tree representation, right?
Yes, sir.
Yes. So number of edges will be traversing from one end to another end. That will be known as the graph representation. You can give any number of edges over there. So that is a graph representation. And this is the thing. And now you want to find out the neighbor node of 0.
4 and 1.
4 and 1. And after giving the edges, you want to find out the neighbor node in your program. That is the thing. First, you are creating a vertices, 5 vertices. It will be not connected vertices. So it means it will create a 5 vertices which will not be connected. And after the vertices, you are giving a vertices element to the vertices, and you are connecting the vertices by use of edge function. That is add edge function, and you are doing an operation. So now you can find out the neighbor node of 0. It will be 4 and 1. And what is the neighbor node of 1?
0 and 2.
0, 2, 3, and 4. Am I right?
Yes, sir.
The neighbor node of 2 will be 3 and 1. The neighbor
1.
node of 3 will be 2, 1 and 4. Yes. The
Yes,
neighbor
sir.
node of 4 will be 0, 3 and 1.
3, 1.
Yes, so this is a neighbor node. So, next class we will discuss about how to create a graph and how to add an edges for that particular graph and how to find out the neighbor nodes of the graphs. So that we will discuss in the next class, right? So as of now, the theory will be completed. So for the 15th unit, this is only one theory part that we are having, and in the upcoming, I hope so, 5 to 6 classes we are going to discuss about the graph, the representation. Now we have completed the representation. Now we will start with the graph traversal. So the graph traversal technique and implementation of shortest path algorithm and implementation of minimum spanning tree. So that we will discuss. That we will discuss in the final topic, the minimum spanning tree. So first you want to create a graph and you want to find out the shortest path from one vertices to another vertices. So that we will discuss along to 3 to 4 classes that we will do the program, right? So suppose the code is there, but time is not there. The code is there. Now you can see this, the vertices. So the code which will be consist of the adjacent node of all the vertices that I have find out here. Can see that the vertices, the adjacent node of 0, it will be 4 and 1 that we have designed a graph, and you have find out that 0 it will be 4 and 1. 0, 4 and 1 will be the adjacent node. For 1 it will be 4, 3, 2 and 0. For 1 we having a 4 edges over here, so it will be 4 vertices will be there, 4, 3, 2 and 0. For 2 there is only 2 edges, so it means 1 and 3. And for 3 it will be 3 edges, that is 4, 1 and 2. And for 4 it will be 3 edges, that is 0, 1 and 3. So that is an output. So this is the first program that you are going to learn in the tomorrow class. So it means we are going to create a edge, create a node, and after that creating an edge, and after that we are finding out the adjacent node for each and individual vertices. Yes.
Okay.
Yes. So any doubts as of now? No. Yes. If you are not having any doubts, you can give your attendance and you can leave now.